Now let's say we have some object with mass m, and it's some height h above the surface of the Earth. Okay, so if we wanted to write the potential of this object, we would say that its potential is equal to the mass times the mass of the Earth times Newton's constant divided by h plus the radius of the Earth, because remember, the force of gravitation acts between their centers of mass. So it's actually this distance, the radius of the Earth, plus h. Okay? But then if we drop this object and it falls and it hits the Earth, then our final potential is going to be the mass of the object times the mass of the Earth times g all over the radius of the Earth. And these both come with negative signs because that potential is negative. Okay, so let's try and get a positive potential. So in other words, let's say we're throwing it up. So in other words, we'll make this our final potential, and we make this our initial potential. So what we really care about is the change in potential. And so this is going to be the mass of the object times the mass of the Earth times g all over the radius of the Earth times minus the radius of the Earth over h plus radius of the Earth, and then minus a negative, so plus 1 for this term. Okay, and so now we'll simplify and get a common denominator. So we see that this is equal to the mass of the object times the mass of the Earth, g over the radius of the Earth, and then minus radius of the Earth plus h plus radius of the Earth all over h plus the radius of the Earth. And so these terms cancel, and so we have something that looks like, so this is just the mass times the mass of the Earth, g, over the radius of the Earth, times h plus the radius of the Earth, and then times h. Okay? But now let's remember something. We're going to have to go back a little bit to the earlier lectures. We said the force of gravity near Earth's surface is the mass times g, where g is the acceleration due to gravity. And we also said that this is the mass times the mass of the Earth, g, all over the radius of the Earth squared. So in other words, we see that g is equal to the mass of the Earth, big G, times the radius of the Earth squared. So let's say we have a situation where the radius of the Earth is much bigger than h. Okay, then this is clearly going to be, approximately the mass of the object times the mass of the Earth, g, over the radius of the Earth squared times h. Well, again, this just becomes, little g, the acceleration due to gravity. So in other words, our change in potential is just mgh. And so this is going to be a formula you're going to use quite often in this class. So this is the change in gravitational potential. This is the gravitational potential if we set the surface of the Earth equal to v equals 0. Then at some height h, the potential is mgh. So those of you who have physics before are probably familiar with this. And if you haven't, you will be shortly, because as you start to work problems, you're going to see this comes up a lot. So now we're ready to start looking at conservation of energy. So we looked at conservation of momentum before. Now we can look at conservation of energy and start seeing what some of the results we get from that are.